Alright, so let's finish up chapter 15 with this video. If the material in that chapter isn't covered in this video, we are not going to cover it simply because we don't have time. Just as a quick reminder, what we've done so far is we've looked at the fact that if we rearrange Newton's second law, we can come up with the principle of linear impulse and momentum, where the impulse exerted on an object is equal to its change in its linear momentum. For that situation, in the absence of external forces, and when we have a system of particles, we find that the impulse-momentum relationship leads to the conservation of momentum, where we say that the sum of the initial momenta is equal to the sum of the final momentum. And we usually use this concept to do impact problems, or what we usually call as collisions. Finally, in the last video, we also looked at something called the coefficient of restitution, which the idea is to really be able to quantify the fact that when two objects impact each other, there's some sort of energy lost in that situation. The coefficient of restitution really gives us a way to sort of see what the effect is on the velocities because of that loss of energy. It also gives us an additional expression that we can use to solve for our unknowns in a problem. So what it is it basically says that the relative velocity after the impact is related to the relative velocity before the impact, and that relationship is through this thing called the coefficient of restitution. The values for coefficient of restitution are somewhere between 0 and 1, including those endpoints, where 0 is the situation where we have a perfectly inelastic collision, where the two objects would stick together so that they wouldn't have any relative velocity after the collision. And when the coefficient of restitution is equal to 1, we have a perfectly elastic collision. In general physics, we recognize that in those situations, the kinetic energy was conserved. All right, so the last thing that we're going to look at in this chapter has to do with angular momentum. One of the applications of this is satellite motion. We find that when objects are traveling around a central object through the force of gravity, they also have their angular momentum conserved. And so we want to familiarize ourselves or reacquaint ourselves with what angular momentum is, and also see when is it going to be conserved. So angular momentum is basically a measurement of momentum about some central point. So we can think of it as the moment of the momentum. So for instance, in this picture right here, we're measuring relative to the origin the angular momentum of the object, which is right here, moving with some momentum. And so the way that we find it, finding the moment of the momentum, means that we take a radius vector, r, that goes from the origin to that object and cross it with the momentum. We can do that through the matrix method. We can also say that the magnitude of this is going to be r mv sine of phi, where phi is the angle between the two objects, so it could be right here, phi. We can also call r sine phi equal to d, which is sort of like our moment arm, and so we could also express the angular momentum as mv times d. All right, so let's think about how we can look at this angular momentum. So for instance, Newton's second law can be written in terms of regular momentum. If the mass is not changing, we can just write it, the mass times acceleration, as also the derivative of m times v with respect to t. Again, we're requiring that the mass remains constant, And so we could call this dl dt. Now, so we've written Newton's second law in terms of momentum. We want to see if we can do something to it to get a relationship that's similar for angular momentum. If you're thinking about the analogous quantities, something that's analogous to force when we're talking about rotational motion would be moment, and then the analogous quantity to regular momentum or linear momentum would be angular momentum. So what we're going to do is we're going to take this, and to get that moment term out, and we'll see later on also the angular momentum, we're going to take r cross this whole equation, which gives us r cross f is equal to r cross dl dt. Now, what we think if I could spell our hypothesis, is that we'll find that the moment is equal to the time derivative of the angular momentum with respect to time. That would make this equation kind of similar to F is equal to dl dt. So is this true? Well, what we have to do is, this is absolutely the moment, r cross F, but is this the time derivative of angular momentum with respect to time? Well, let's figure it out. So angular momentum is r cross mv, so let's take its time derivative. Using the product rule. So at first it looks like we have a problem. It looks like, oh, well, I see two terms here for the time derivative of angular momentum, but I only see one in my expression above, so am I wrong? But if we take a closer look at this, we should understand that the cross product of velocity and momentum is going to be 0 because v is parallel to mv. And so their cross product would be 0 because of the fact that they're parallel vectors. And so indeed, it is true that the moment is equal to the change in the time derivative of the angular momentum, just as we hypothesized. All right, so I should have had more room, so let's move on. So if we have that, we can also, just as we did with regular impulse and momentum, we can rearrange this and have the moment times dt is equal to dh, and we can integrate both sides. We'll call this the angular impulse, and this is going to just be the change in angular momentum. Again, a very similar expression to what we looked at the beginning of the chapter, but just for angular quantities. And so this is a way where we could think of like, oh, how do I change the angular momentum of an object? Oh, I have to exert a moment on it for some amount of time. See how it's very similar? If the sum of the moments is equal to 0, then delta H is equal to 0, and H1 is equal to H2. All these things are vectors. I'm forgetting to write. This is conservation of angular momentum. And this is the type of thing that we use to understand, skaters spinning more quickly, the demo with a person on a rotating platform with weights in their hands, or also the motion of the planets. Basically what we're saying is, in a system where there isn't any external moments acting on the system, and if it has some angular momentum, that total angular momentum will remain constant throughout its path. A good example of the type of force that can be acting on an object but not giving it a moment is a central force, particularly gravity. Because if you have a central force, the radius vector and the force vector are anti-parallel to each other. Therefore, the moment due to r cross f is 0, and therefore the angular momentum will be conserved. And that is that for the chapter. We'll do some problems on Friday, and hopefully we'll find that this isn't too bad.